We're now going to face our first from-scratch solving process for a second-order differential equation. We're going to see how straightforward this is. We're asked to find the general solution to y double prime plus 5y prime minus 6y equals 0. So first checklist, linear. Check. Homogeneous. The right-hand side is 0. Check. And coefficients are constant. Constant coefficients. Check. So what that means we can do is we can try y equals e to the rx as our solution. And what we're going to see there is we've done this once in the general case, so we're going to jump straight to the answer here. When we take y double prime, we'd get an r out and another r out, we'd have r squared. For y prime, we'd have an r times e to the rx, but we're going to factor that out. In fact, let's write it this way. If we were to do this completely, y would be just e to the rx, we'd have negative 6 out front, and if we factor out all the e to the rx's, we would get this expression here, which we can distill down to the zero part, which is our characteristic equation. This is going to be something we're going to see a lot of moving forward. So this differential equation turns into this if we make the assumption that y equals e to the rx is our solution form. Looking at this quadratic, we can solve it by factoring, and if we're careful with our factors, we have a product of negative 6, sum of plus 5. If we factor that to plus 6 and negative 1, then we get that form there, which means r equals negative 6 and r equals plus 1. Our solutions, I'm going to try to be very clear here. These are solutions to the characteristic equation. This is just a polynomial. When we solve it, we get r equals negative 6 and plus 1. But the fun part about the differential equations is that r equals negative 6, that's what goes up in the exponent with the e. So y equals e to the negative 6x, call that y1, and y2, which will be e to the 1x, are solutions to the original differential equation. That's where we get our real payback. Our original differential equation at the top here. And it couldn't get any easier than this. We can do a little check, but these things are linearly independent. y1, y2 are linearly independent. And so right away, we get the general solution. c1 e to the negative 6 plus c2 e to the x is the general solution. That is about as straightforward as it gets. We had a second-order differential equation. We had to solve it. We had to find two solutions. Well, we did that by taking a guess, an informed guess, but a guess nonetheless, that y equals e to the rx would work. When we did that, we found that two values for r would work, so we can build two solutions. And we saw through the earlier theory that two solutions can be combined as a linear combination to get the general solution to the second order system. So it's nice. It's really nice to be able to do that. So that's your first example of a first start to finish solving of a second order differential equation. Now, can we generalize that? Well, of course, if we have this general property r1 and r2 and they're different, notice we're going to say there's two distinct roots, then right away we can jump to the general solution as e to the r1 x plus some other constant e to the r2x. Well, it turns out that that's pretty straightforward to show because our assumption was that y equals e to the rx is a solution. And so by finding these two distinct values, y1 equals e to the r1x and y2 equals e to the r2x are definitely solutions to the equation, the differential equation that is. And if that's the case, The only other thing we need is that they be linearly independent. So our e to the r1x and e to the r2x linearly independent. Well, again, we just check our Wronskian. So Wronskian of e to the r1x, that's a lot of subscripts. So try to write these out carefully. That's the determinant of some matrix. The matrix is built up out of the original functions and, need a little more room here, their derivatives. So we're going to take the derivative of each element in each row. We're going to get r1 e to the r1x and r2 e to the r2x. We'll take the determinant of that matrix. And again, if this determinant is non-zero, that means somehow this matrix has a unique solution when we set it up as a part of an equation. And so our test is Wronskian not equal to 0 means our two solutions are linearly independent. All right. Well, again, we take our product there and there. Our Wronskian then is going to be e to the r1x times r2 e to the r2x minus r1 e to the r1x e to the r2x. And that, all the terms have an e to the r1x and e to the r2x, and we can combine those into a combined exponent. The only thing missing is the scalar multiplier there, r2, r1. And so this is never equal to 0. It's an exponential. And this is not equal to 0 so long as, oh, we said this up front, as long as r1 and r2 are distinct or different. And as soon as we say that, characteristic equation has two distinct solutions, r1, r2, then bang, we have one solution and two solutions, and so this would be the general solution by simply combining with the e to the r1x, e to the r2x with coefficients out front. So this is fantastic. The case that we just saw in the last example, where we found the characteristic equation and then found two distinct roots, we can jump immediately to the general solution. We know exactly how that's going to work, and it's going to work for any case where we get r equal to two different values when we solve the characteristic equation.